Hello and welcome to the second workshop of the ABRF iPRG 2022 Cloud Computing series. My name is Melanie Föll. I'm a junior research group leader at the Institute for Surgical Pathology in Freiburg, Germany, and a visiting scientist at Northeastern University in the lab of Olga Witek. Today the topic is performing shotgun proteomics analysis in Galaxy using MaxQuant. Today's workshop has two major parts. First, a theoretical part with an introduction into Galaxy, its application to proteomics, and special features and technical backgrounds. In the second part is the hands-on analysis of the shotgun proteomics dataset in Galaxy. That's the same dataset that was also used in the last workshop. And a tip for proteomics newcomer, I've made a video with a quick introduction into quantitative proteomics, which is available on the shown YouTube link. So what is Galaxy? Galaxy is a web-based platform for computational biomedical research. It's community-driven with more than 200,000 users worldwide and many contributors to the Galaxy framework, to the Galaxy tools and the Galaxy training materials. Galaxy is open source. It currently has more than 8,000 ready-to-use tools and was cited more than 10,000 times. Galaxy is compatible with laptop, personal computer, high-performance computing and cloud computing. More than 125 public Galaxy servers are currently available for free use. The core values of Galaxy are accessibility, reproducibility and transparency. Galaxy has a graphical user interface and therefore there's no need to have any programming skills to use it. The tools are also pre-installed, you can directly run them, and to access Galaxy only a web browser and internet connection is necessary. As I said, Galaxy is open source and runs the jobs on public clouds. In terms of reproducibility, the Galaxy analysis histories, they store all the metadata. So also the tool versions are controlled and the tool version, tool name and all the parameters and much more information is connected to each analysis step. The tools can also be connected into standardized workflows and both the analysis histories and the workflows can be shared either privately with collaborators or publicly, for example, as part of a publication. So more than 8,000 tools are currently available in Galaxy, and in theory any open source tool can be integrated. Galaxy derives more from the genomics area, but currently covers all typical omics like transcriptomics, proteomics, metabolomics, and also other areas such as chemistry, statistics, ecology, and even climate research. So there are nearly 400 proteomics tools in Galaxy currently, and they are available through many public Galaxy servers. The European Galaxy server is one of the main public Galaxy servers and has many proteomics tools installed, and these tools can be run and computed on all the computing power of the European Galaxy server, which are more than 9,000 cores, 60 terabyte of RAM, 4 petabyte of storage, and on the server are 2,900 tools currently installed, and more than 50,000 users are making use of this giant computational resource, which is funded by the funding agencies and shown at the bottom. So this is the graphical user interface of Galaxy. It has 3 main panels, and the data can be uploaded from the computer via an URL or via FTP. And there are also Galaxy tools that directly download data from public repositories, for example from UniProt. On the left-hand side, the panel is the tool panel. Here the pre-installed tools are available. They can be either searched or you can look at the different categories of the different tool categories and search for your tool manually. Then in the middle is the main panel, where typically if you click on a tool, it opens there and you can specify all the parameters. And these are the proteomics tools that are currently installed on the European Galaxy server. So there are quite many. But in addition, there are also interactive environments available. So for example, you can switch from Galaxy directly, even with transferring easily your last Galaxy dataset into either a Studio or Jupyter Notebook or more specialized interactive tools. And afterwards, you can quite easily transfer your output from these analyses back into your Galaxy analysis history and continue with classical Galaxy tools, the analysis. So here's how MaxQuant looks like in Galaxy. So we more or less mimic the sections that are also available in the original MaxQuant graphical user interface. So input options, search options, protein quantification, the parameter group parameters. And what is special is that we have integrated the PTXQC software, which generates an automated visual quality report about the raw data and also the success of the MaxQuant analysis. And then different output options can be chosen. So the advantages are that MaxQuant is pre-installed, so it can directly be used. There are even two versions, so the MaxQuant tool I showed you, where you can manually specify the parameters, but there's also a MaxQuant version that uses the MQ-par XML, which is the MaxQuant parameter file. And there you can use this parameter file to specify the parameters for your MaxQuant run. Also, different versions are installed in Galaxy, and you can switch back or just switch between the different versions. And after running MaxQuant in Galaxy, all the parameters and tool version and so on are stored as metadata in your analysis history and allowed to retrace what was done. And another advantage is that MaxQuant on the European Galaxy server means that you can make use of free cloud computing resources. So your local computer is not blocked at all. All the analyses are running in Galaxy, and also you can combine MaxQuant with many other Galaxy tools, for example, for visualization or statistics. For the tool integration in Galaxy, one writes a so-called XML wrapper, which specifies the inputs and outputs as well as the tool parameters, all the tool dependencies that are needed for the successful tool installation are specified in a contour recipe, and out of this biocontainers are generated for each tool. The Galaxy tools are available then via the Galaxy toolshed, and from this central app repository, all the Galaxy servers that exist can decide which tool they install on their Galaxy platform, and the European Galaxy server has installed most, if not all, available Galaxy proteomics tools. But they are also available on other public Galaxy servers. And then the third tool panel on the right-hand side is the analysis history. So every output dataset that is generated by a job is stored separately with an own number and cannot be manipulated. It can only be deleted. And so an analysis history that contains also all the metadata. So the metadata is available for each individual file in the history. And so the analysis can be really reproducible. Additionally, Galaxy is also a workflow management system. There is a workflow editor where one can connect different tools together into a workflow, and afterwards the workflow can be run several times, also like in a standardized way. so that the same analysis can be automated. So what's happening behind the European Galaxy server is that there's a Pulsar Network which allows different computing centers across Europe and even the world to share their public resources with the European Galaxy server. So all these different computers or clouds are connected and are available for the jobs running on the European Galaxy server. There's also the Galaxy Training Network, currently covering 28 different research fields with more than 285 tutorials, and the availability of trainings are growing over time. Currently for proteomics there are 27 trainings available, and they cover protein identification and quantification, multi-omics analysis, for example, metaproteomics and proteogenomics, post-processing analysis, and also very special techniques, for example, mass spectrometry imaging. Here are many links and resources to learn more and get involved into the Proteomics Galaxy community. And now we switch to the hands-on part. So for the hands-on analysis in Galaxy, we will use the same dataset as was used last month. So there are two different mixtures of human and E. coli proteins, and each mixture was fractionated into 24 fractions and analyzed as triplicates on an LTQ orbit trap. And with that, please go to the European Galaxy server, and if you do not yet have an account, please register, because then all your analysis history will stay connected in your account and you can at any time come back, and it also allows you to use the workflow management system of Galaxy. Okay, then see you soon for the hands-on part. For the hands-on part, we log into the European Galaxy server, and you may see the three main panels now. And on the right-hand side, we have an empty history, which we are now going to fill. First, we rename the history. We click on this pencil and then give it a name. I use Cloud Computing Workshop in Galaxy. You can write further annotations or use a tag for the history, and then we click on Save. Now we need to get some data in. The dataset is in the Pride database, project 279. We scroll down and click on Project FTP. And here we scroll down and open the readme.txt. And we will not analyze all the raw data, but just the ones which is consistently named, so that we can use special Galaxy features which we can apply to multiple files. So we copy line 22 to 86, and this should include the first 11 fractions. So we had 24 fractions in total, but we will stick to the first 11 fractions. I copy this, go to the Upload Data button in Galaxy, I click on it, and here we have the Paste Fetch Data option. I click on that, and into the big box I paste the information. So we will now generate a text file as our first file in the history that contains an overview about all the data sets. So we call it file overview. This field gives the name to the data set in the history. Then Galaxy is automatically trying to detect the data type, but if we know it for sure, we can already select it ourselves. So this is a tabular file. This means it's a tab separated file. It's a Galaxy specific file type for TSV files. Here we also go on settings, onto the options we choose, convert spaces to tabs. to be sure that we obtain a top separated file. Then I press start and close the upload manager. So the file was gray when it was waiting to run. It turns yellow when it's running, and afterwards hopefully green. In case there's an error, it would turn red. And in this file we have now an overview about the raw files from this project. We have 65 lines, and pressing on this I button we can open the file and have a look at it. So we have different columns. Here this column is the file name, here's the URL. Yeah, there's 2 more columns that are not really relevant. So here towards the end of the file name we see that we have 03, 02, 01. So these are the 3 replicates that were measured, and the first step now is that we select only the ones, the 3rd replicate we use for this exemplary analysis. So we copy this 03.raw and we choose the select tools. So we go to filter and sort and select lines that match an expression is the right tool. I click on it. It automatically loads the only available file in our history, and we want to keep all the lines that match the 03.raw. We don't have any header line, so I can just execute it, and this generates a new entry in the history. And as you can see, the name of the file is typically the tool name, and then it says on which data set from the history it was started. And we are doing this procedure now mainly to prepare the sample cohort for the MaxQuant run. And in MaxQuant we need to specify an experimental design template in which we need to specify the name of each file. It has to match exactly the name of the raw files that are put into MaxQuant. So we have this already here in the second column, and then we also need to have the experiment. So in our case experiment would be either E. coli 10 or E. coli 30, and then we also need to have the fraction. This is here specified by frac 01, 02, 03 and so on. Unfortunately also here the naming is not consistent. Here's for example frac 4 and frac 5 without a 0, and therefore we will in the next step replace frac 0 or remove frac 0 and also frac, so that the that we obtain just a number that specifies the fraction. And we will do this with a replacement tool. So we will later use the second column as a name, and we will extract the experiment and the fraction number from this third column with the URL. We do this by going to text manipulation section and scroll quite a bit down to find a tool called replace. But there are many replace tools. We need replace text in a specific column. That's the right tool to use. And we automatically have loaded now the latest tabular file from the history, the second one, which is fine. So, but we could also switch to the first one. Just Galaxy selects always the latest file that fits to the input file type specifications. So we run this tool on the second file where we selected only the third replicates, and choose now column 3 where we have the whole URL, and we want to find the pattern frac 0 and remove it, and this we do by replacing it with nothing. Then I click on insert replacement, again column 3, this time only frac, so we have frac 0 and frac. I replace it with nothing so that it's removed. And then the last step is we go to column 3, and there were, as we can see here, there are always underscores between the different data that we need. And so we replace the pattern underscore with \t, which inserts a tab. So we generate new columns now. And in the next step, we decide which columns we would like to keep. So there's a tool that cuts out only columns of interest. It's called cut column from a table. And if we open it, we see we can just specify the column numbers which we would like to keep. And for this, we need to wait until this step has finished. Now we can view it. And we can note which columns we need. So we need column 2 with the file name. We need 2, 3, 4, 5, 6, 7. We need column 8 with the information about the experiment, E. coli 10 or 30. And then we need here what we generated the number for the fraction. And now we see that it's it's now consistent, just a number, and we can work with that. So that's column 11. So we open the cut columns from a table tool, and we specify the columns we would like to keep. Column 2, column 11 with the fraction, and column 8 with the experiment. And we automatically have the right tool at the right data set selected here. Then we can execute. And for the experimental design template for MaxQuant, we need not only the name, the fraction, and the experiment, but also the PTM status. And we are not looking at PTMs here, so the PTM status is false. So we have the 3 columns, and now we are adding a new column. We need 4 columns. And this can be done here. Add a column to an existing data set. So that's all the later tools we are using now, except for the first one, are in the section text manipulation. Add column to an existing data set. Yeah, we have data set number 4 with the cutted columns, and we add the value false as a new column to all lines. And I forgot to show you before, but if we go into MaxQuant in Galaxy, we use this normal MaxQuant tool. Here's the option to specify this experimental design template, and this is needed in our case because we have multiple fractions for the same experiment. It further says detailed instruction, see the help text. The help is always down below the tool. Here's the experimental design template, and here it is for raw files. And we already have a column with the name, which needs to match exactly the name of the input raw file for MaxQuant. Then the fraction and the experiment and the PTM status. So what we are needing now is we need to have this header line. I can try to copy it from here. And then we go to upload data, paste. We put this in. We give it a name, it's the header line. We make sure that it's in the right format. And I think it's also good to say convert spaces to tabs. Maybe I remove this to make sure that there's one space in between, and this will be converted to tab. And then start and close. We can look at the result from the last step. So we have now 4 columns. We added the false information to each line, and now we should have a header line that has also 4 columns. And then the last step we need to do is to fuse the header line on top of this table that we have here. Perfect. The header line has also 4 columns. So we close here the search and go back to text manipulation and choose concatenate datasets tail to head. So the first dataset we use is the header line, and the second one is number 5, add column. And with this step we can combine these two. And now we already have the first input for MaxQuant, which is this experimental design template. And the MaxQuant GUI, you can specify this interactively, like manually in a table, but in Galaxy it was the easiest to have it as a separate file, especially if you have high throughput experiments with many fractions and experiments. It might be even easier to just generate such a table from your file names than to manually insert it. We rename it. For renaming, we click on this pencil here and rename this dataset into experimental design template and save. What we also need is, of course, a FASTA file. So this we get in the get data section. There should be the protein database downloader. So we download from the UniProt database. We need human, and we only take the reviewed datasets and the reference proteome set we leave. And I click execute. And if you want to rerun a tool in Galaxy with the same or similar parameters, you can click on it, and there's this rerun button. And if you click on the rerun button, the tool loads exactly in the same tool version and with the parameter that you specified. So we want to have the same parameters, reviewed only and reference proteome set, but this time not for human, but for E. coli. And then, after changing this taxonomy, I can just execute and obtain now the protein sequences for E. coli. We have two databases now, and in Galaxy we can quite easily merge them together. I think it's merge FASTA. It's not always easy to find here. The search is also not perfect. Where is it? So there are many tools using FASTA and merge. I think I have it in my favorites as well. FASTA merge files and filter unique sequences. Let's see. We would also find it like this. Here it is. Okay, so if you search for FASTA merge files and filter unique sequences, you will also find it. And here we just need to insert the two databases. So we take the number 8, which was human, and number 9, E. coli, and we say that the accession numbers should be defining what is an individual protein sequence. And then I hit execute, and then we have the merged E. coli human FASTA database. So the last input files that we need to load into our history are the raw files. To get the raw files relatively automatically, we go back to file number 2 and open it here. And here in the third column are all our URLs that we will need. And so I just do Control A to copy everything. Control C, go to upload data. And this time we don't do the regular upload, but we do the rule-based upload. I paste everything here. And we don't want to upload individual data sets, but we would like to upload collections. This means that all the data sets are connected into one entry in the history, which is linked back to all the individual data sets. Then we go to build. And now we have to specify some options. First of all, it says we need to name the collection. That's here. I call it the raw files. Also, it's good if we specify the raw file type here. So it's thermo-raw type in Galaxy. And now we need to specify which column has the URL and which column has a list identifier. We click here in the middle of the text to specify this. We add a definition. List identifier is B. And the URL is C. So what you can do is you can also use deferred URL. This means that the raw data sets are not loaded into your history. They are just linked. And later, when you run MaxQuant, you have just the MaxQuant results files in your history available, but not the raw files. And this saves a lot of your quota on Galaxy. So I will do the real URL in a classical way, and URL is in C. This means that we are now going to really download physically the data sets into Galaxy here. And then I press upload. And because I'm now physically loading the data sets, that can take quite a bit. Okay, now the files are loaded. We have a new entry. It says raw files, a list with 22 data sets. And when we click on this collection that we generated, we find all the individual 22 raw files behind this single entry in this history. So now we are finally ready to start MaxQuant. We can use the search option to find it. So it starts with the input options. We have a thermo raw file, however the raw file is defined later. So for FASTA file we have our merged single input file. Here we have different identifier path rules, and the description how you can modify them is again in the help section of the tool. Here in the search options we specify our experimental design template, number 7 for me in the history. Then we keep most of the MaxQuant parameters as they are. Minimum unique peptides we switch to 1. And match between runs we say yes. We would like to transfer the identifications across the LCMS runs. And then we go further down. And here's now in this parameter group option is the input option for the raw files. It says we don't have thermo raw files, however this is single data sets, and single data sets in our collection are hidden and therefore they cannot be used as input. And so we click here on dataset collection, and now we see our collection and can select it. We leave all these options except for the quantification method. Here we just specify label-free quantification, and as you can see MaxQuant can also support different other quantification methods. We leave the parameters by default, and then we generate a PDXQC quality report. We leave everything as it is and then output protein groups and peptides, maybe also evidence. And then we press execute, and this can take quite a bit of time. So we need some patience, but I will also provide the result files from MaxQuant so that you can analyze, continue the analysis without having to wait for MaxQuant to finish if you're a bit in a hurry. MaxQuant is finished now. We have 4 new entries in our history and we are going to have a look at them. The first is the PDXQC quality report. For our 22 files we have several performance measurements, and following in the document are many different visualizations of these, for example here the contaminants per raw file and so on. So then we have the evidence file. So this is the feature level data. We have about 250,000 lines. This file is important if we would like to follow up with statistical analysis on MS Stats, which is also available in Galaxy. Then we have the peptides file. Around 19,000 peptides were found here. And we have the protein file, on which we will focus now, with 2,800 proteins roughly. And we inspect this protein groups file. So here we have the protein IDs, and we can see that we have the reverse proteins still in our list. So the first thing we are doing soon is to exclude them and remove them from our data. And if we go further on, there are some intensities. So we will use the label-free quantification intensities of E. coli 10 and E. coli 30. And unfortunately, currently the column, the header with the column number is broken in Galaxy. So I counted for you. This is column 44, this is column 45, and we are soon going to extract them to have a smaller tabular file to work with. So the first step we are doing is we're going to text manipulation again. We're going to filter and sort first, and we select lines that match an expression. And we need to choose the right input. So it's protein group input, and we would like to select lines that are not matching the decoy proteins that are labeled with this prefix ref. And we have a header line, so we can confirm here in this preview. The first line is a header line. We would like to keep it. Yes. In the next step, we can already continue. We use the same select lines tool, and we use it on this newly generated protein group dataset. And this time we want to match human, because as you may have seen here, we have the information with each protein ID, at least if it's not a contaminant, it says that it's either human or E. coli. So we keep header line, and we do exactly the same. So I use the rerun and keep only E. coli from exactly the same input data set. So this is already done. We have 2,800 lines left. So these are then the proteins. Contaminants are still included, but we will keep them in. They did not have high intensities as we have seen in this PDXQC report. So we have around 1,800 human proteins, and as the file name is not really informative and it's a lot of work to rename it every time, what we will use is a tag. So we start the tag with a hashtag and then write human. And when we write the hashtag in front of our tag, the tag is propagated every time this data set is used. The tag is propagated, and so it continues throughout the whole analysis, and we will now always know which data comes from the human proteins and which comes from the E. coli proteins. And now we still have all columns, but we don't actually need them. So now we go to text manipulation and cut columns from a table. And the columns that we are interested in is column 2 with the major protein IDs. Then we said column 44 and column 45 were the label-free intensities. And by clicking on those multiple data sets and then holding the control, I can select multiple input files. And because this operation has to be exactly the same for both the E. coli and the human file, I can do it together. So executing this now starts 2 jobs, and I get 2 new entries in my history, one for human and one for E. coli. The next step is that we would like to calculate the log2 fold change between the E. coli 30 and the E. coli 10 condition. And this we do with a compute tool. So that's already here, the compute on rows tool. Maybe we before inspect one of these files so that we know how it looks like. So now we have 3 columns left. First we have the protein ID. Second column is E. coli 10 and the third column is E. coli 30. So we are now calculating the ratio column 3 to column 2 and then take the log2 fold change from that value. So I use the tool compute on rows, and this time I do it step by step. So first the human, then we have a header line. Yes, I insert an expression, and the expression, as we said, is the log2 fold change from the ratio column 3 to column 2. And now we have to give this column a new name, and that's why we do it not together for both files, because these are now the log2 fold change human. And we also have to do an error handling. So it may be that an expression cannot be computed for a row because we have also zero intensities, and we just say skip the row, and then I can execute. And then I just repeat the same step for E. coli, compute on rows. I choose the right input data set, so the last E. coli data set from my history. I have, yes, a header line, I insert expression. It's the same log2 fold change calculation as before, but this time the new column is named log2 fold change E. coli. And for error handling, we do the same. We skip the row if calculation is not possible. And now, only for reasons about which visualization tool we are going to use, we have to extract the log2 fold change column of both data sets. So this is now column 4. So we added a new column with the log2 fold change here, and it will look the same for the E. coli. So we are now using the cut tool again. We cut column 4 with the log2 fold change, and again we do it on multiple data sets at the same time. So we do it on the 2 compute outputs. And now we bring both data sets into one tabular file by using the paste 2 files side by side tool, which means that we are just putting the 2 single columns that we have now together in a new tab separated. So here it says tab separated file. And then we are ready to do a histogram as a final visualization. And we use the histogram with ggplot tool. And we use paste dataset as input, and the plot title, we just say the distribution of log2 fold change. That's all we need to do. And then we can execute our final step, in which we are now plotting the log2 fold change distributions between the E. coli 30 and 10 datasets separately for the E. coli and for the human proteins. So it's going to run. So here's a refresh button if we are, but it seems to refresh every 3 seconds. So there's probably no help in clicking the button. You just need some patience here. Okay, we can inspect it. So we see we have a red fold change distribution for the human proteins and a green one for the E. coli proteins. The E. coli proteins are around log2 fold change of 1, which is not exactly the 3:1 ratio, which would be more towards 1.6 log2 fold change. But as we have seen in the TPP workshop, E. coli 30 have higher intensities than E. coli 10, and there are reasons why it's not exactly the 3:1 ratio. And the human are around minus 0.8, which I think makes also sense. So now we go and share our history. Here is an arrow. And if we say share or publish, we have different options. So here we can share with an individual user. We need to know the email address with which this person has registered in this Galaxy server. Then we can share it privately. We can also share it privately by generating a link. So only everyone who is having this link is able to see the history. And generally, if I share my history, no one can manipulate it in my account. So everyone can only inspect my history, or to work with the history, you need to import it into your own account, and only then you are giving permission to change something. So I'm safe in sharing my history. And I will also make the history publicly available here. And then this is available in the published histories. You can also go there through shared data histories. And then you can see Cloud Computing Workshop in Galaxy is shared from me, and everyone is now able to see it. In the next step, we will also extract the workflow. So all the analysis steps we have done, we can now put into a workflow, because apparently it worked nicely. So maybe we want to do it again. We name it protein inspection, exactly. And here are all the steps. We could also unselect some of them, but we would like to include them all here. So I say create workflow, and we can immediately edit it. So we are now linked to the workflow editor. And here's the overview view. So there are a lot of steps that we have done. And going to the left side, we see the input data set. So we had a file overview, which we needed for the experimental design template for MaxQuant, and similarly the header line. Then we had the raw data set collection, and also the UniProt are downloads for human and E. coli are listed as inputs. And here in this editor, we can manually move the different boxes around as we want. Once we click onto one such a box, the typical outline of the tool shows up here on the right hand side. We can also enlarge it, and we can adjust all the parameters, so directly from this workflow editor menu. We can also you can delete lines like this, and then you can build a new line. We can also rename. So here, if we rename the label, so we can say removal of reverse proteins, for example, and then we immediately see not the tool name, but what was actually happening. But we could also leave the tool name and just write here into the annotation that here we are selecting only human proteins. And if we spend a lot of time adjusting our parameters and we would like to do something in parallel, one can just click the duplicate tool, and then there's also an option with tool recommendations, so which tools are typically used after the select tool. So here's the workflow up to the histogram with ggplot. And what is special in this workflow parameter settings here on the right hand side is that we can also, here it is, configure our output. So if I click on this, I can say the output of this step should have the following label, or it should have the following dataset name, or I could also here add the human tag. And then from here on, as we did it, the human and also the E. coli tag would be available and used throughout the next step of the analysis. And then this workflow can be saved and then appears in the list of workflows that we have here. So in the I've also shared the workflow already publicly for the peptide follow-up. So here it is. So this is for MaxQuant peptides. We can immediately run it, or in case we would like to manipulate it, you would need to import it and then in the workflow editor make some changes. So for now I just press run. And now I select the peptides file, so I can type here MaxQuant peptides and run the workflow. And I would like to show you the workflow. So I first started it because it takes a bit of time. So now immediately all the workflow steps are loaded into the history. Going to the shared data workflows, we can, we cannot view it, but I can view it in my workflow. So here peptides. If I go to edit, I'm in the editor again, and we can view what is happening. So MaxQuant peptides goes in. Again, we do the same step as for the proteins. We remove all the reverse proteins. We then select the E. coli and the human proteins. We cut out only the relevant columns. So in this case, I also cut out the peptide sequence and also the corresponding protein ID. Then we computed the log2 fold change. Here we did a separate histogram on E. coli separately and here on humans separately, which we did not for the proteins. But then we also cut out the log2 fold change column, paste them together, and then do the histogram on them. So to go back, we can also just click the Home or the Galaxy Europe button. Yes, I would like to leave the page. I just moved maybe a few boxes, but nothing I would like to save. And here we are running now, so we have more time. One more thing, if we start a workflow, so let's go to the workflow again. There's another option which we didn't use. So we would use the peptides. Here we can expand to the full workflow form. And if we do this, we see all the different steps. So this information was lost. So we can double check that everything is as we expect. We even would have the possibility to switch it last minute. And there's an option to send the results directly to a new history. And then we could just give this a new name. And then all the steps that are calculated from this workflow are separate from the input analysis histories. And that can be quite helpful to have one history with all the raw data and input data, and then to start the workflow and send all the results into a new history. And that's especially helpful if Galaxy workflows are used to test several analysis pipelines, so that every output ends up in a new history and can be separately inspected. And then it gets less, the history gets less crowded. Okay, so the last step is running. We are waiting for it to finish. And it's green. We can inspect it. So for the peptides, we see that the log2 fold change distribution is a bit larger, and it's also a bit different. So we here the peak for human is around 0, and for the E. coli it's around 2. Maybe a bit more realistic. So the LFQ protein intensities there are quite a lot of normalization steps going on. So that's why we have different outcomes now between the more or less raw peptide intensities and the protein intensities. That's the end of the Galaxy workshop. I hope I could show a bit interesting features of Galaxy, and that it's really nice to work with data sharing and building workflows, and just having a easy to use graphical user interface, even though maybe the search of the tools is not always the easiest, but there was this option which I used. So if you have a tool that you use a lot, there's a star and you can add it to your favorites. And then if you add it to your favorites, you don't need to search the whole nearly 3,000 tools now on the European server. You can just go to your show favorites, and then somewhere there it should appear. Of course, I can't find it now. That's the effect of showing things. But in theory, if you click on here, it's maybe I'm just blind. It should appear somewhere in this favorite list. But of course, if the favorite list is too long, it also gets quite crowded. Okay, so that's it from me. I'm very happy to answer your questions during this week and also on Friday in the final Q&A live session. Have fun with Galaxy and see you!